Welcome to the course Adaptive Signal Processing. This is lecture number 8. From last two videos, we are discussing properties of autocorrelation matrix, that is capital R. This is the third part. Here we'll discuss more about eigenvalue decomposition. I'll give some application where we can use this EVD, right? So if you enjoy these videos and if you think that this type of courses will be useful for you and you are expecting some videos, more videos on this topic, then you can subscribe this channel and you may like this video if you really enjoy this one. And I request you to share these videos to your known persons who may need these videos. I'll be happy if anyone is getting some advantage from my videos. Now, in previous lectures, we have discussed total 8 properties on autocorrelation matrix capital R. And I've said that capital R is symmetrical. Second property is R is to Ablich. And third property, R is non-negative definite matrix, or it is called positive semi-definite matrix. Fourth one, eigenvalues of R are all non-negative and real. Then we have discussed fifth property, that if two eigenvalues lambda I and lambda j, they are distinct, then corresponding eigenvectors qi and qj, they are orthogonal to each others. And sixth one says that if all the eigenvalues are distinct, then we can form a matrix capital Q where you will find the eigenvectors in column-wise form. This Q0, Q1, Q2, Ql-1, all are eigenvectors. So this Q matrix will be orthonormal if all the eigenvectors are having unity norm. It implies that Q transpose Q will become identity and Q times Q transpose is also identity, right? And seventh property, we have discussed that we can express capital R as Q times capital lambda times Q transpose, and this is called eigenvalue decomposition. And here you know that Q is that matrix containing all the eigenvectors in column-wise form, and capital lambda is the diagonal matrix containing all the eigenvalues in its diagonal elements. This lambda 0, lambda 1, lambda 2 up to lambda L-1, these are in diagonals. Now off diagonals are all zeros. This is your capital lambda. And Q transpose is transpose of Q. So R is basically product of these three matrices. One is Q, capital lambda, and Q transpose. And in this course, we will be using this eigenvalue decomposition method frequently to analyze adaptive algorithms. Okay, so in this video also I'll be discussing more about this eigenvalue decomposition. And the last property I discussed last time, the trace of R is equals to sum of all eigenvalues. Okay. Now, let us start with the eigenvalue decomposition. Capital R is expressed as the product of these three, Q, capital lambda, Q transpose, where Q is this matrix containing all the eigenvectors in column-wise form, and capital lambda is a diagonal matrix containing all the eigenvalues in its diagonal only, and off diagonals are zeros, right? Now, first I will consider one recursive equation, Wn plus 1 equals to alpha times Wn. So we'll get this kind of recursive equation frequently in our course. And here the objective is to show that this Wn will converge to certain level. So in this case, it should converge to 0 level with proper condition on alpha. Okay, that we used to investigate. But here we want to mention one thing, that don't be confused with standard adaptive algorithms. Though I have used the same W form here, but be careful. So thus I want to discuss more about here. So you understand that we have said that we are going to consider one system identification problem where we'll have one unknown system. Suppose it's one tap, that is your W0. So the input is xn, right? And this Wn is the unknown system coefficient, and it can have one observation noise, that is your Vn. Then this is called desired signal Dn. And to estimate this W0, we will be using one filter. So it is also one tap. Suppose I'll consider in Wn. Okay, this output will be calling as y of n. Then these two will be compared. This is plus, this is minus, and then that difference is the error signal En. Using this error signal, we'll be tuning this Wn. So generally, this Wn will take this kind of update rule, that Wn plus 1 equals to some Wn plus some correction term. Okay. These correction terms depend on the algorithms. In least mean square algorithm, it is a mu into En into xn vector. Okay, that will not discuss right now here. But here the objective is to say that, okay, this Wn is approaching to W0, not exactly Wn. So what I will say, that first we will compute the difference. Okay, this Wn minus W0. This is called weight deviation. Okay, this weight is deviated from this optimum 1 W0. This is the gap, and its expected value, basically we want that it will approach to 0 level as n is approaching to infinity. N is approaching to infinity, and it should be equals to 0. Okay, so here in our cases, what I want, that this quantity should be equals to 0, and we'll show that this expected value of Wn plus 1 minus W0, that can have one recursive rule, some alpha kind of expected value of Wn minus W0. So we'll discuss this thing in detail later in adaptive algorithms, but here for simplicity I want to avoid all the writing this part expected value and this W0, all those things. Thus just simply I have considered one variable, random variable W, but there is no connection with this W. Okay, be careful. Okay, but I want to show that if this kind of recursive equation is there, then this recursive equation will converge to 0, under one condition on alpha. That only I wish to investigate right now. I hope it is clear. So please don't be confused with standard adaptive algorithms right now. We are not considering the adaptive algorithms. We are considering only one variable W, and that is having one recursive rule, Wn plus 1 equals to alpha times Wn, and we wish to show that when n is approaching to infinity, this Wn is going to 0. Okay, fine. So this W initial value is suppose given, W of 0 is given, initial value is given, then will this Wn converge to 0? And what condition it will converge to 0? Okay, that I want to discuss. So what we'll do, we'll start with this equation, Wn plus 1 equals to alpha times Wn. And this Wn again I can replace by same rule, alpha times Wn minus 1, previous only, because Wn plus 1 is equals to alpha times previous 1, Wn. Similarly, Wn should be replaced by alpha times Wn minus 1. Thus, you will get alpha squared Wn minus 1. Again, this Wn minus 1 I can replace by alpha times Wn minus 2, like this. So you will get alpha q n minus 2. So in this way, what you will get? You will get alpha to the power n plus 1 times alpha w to the power 0. Okay. So this w of 0 is the initial value, and this is your power w to the power n minus n plus 1. You see here alpha q, here it is n minus 2. That it is. So if it is n minus n is 0, in that case it is n plus 1, right? So the relation we are getting that this alpha n w of n plus 1 will be alpha to the power n plus 1 w of 0. So this part will become 0 if alpha is within minus 1 to plus 1. Then only this power will vanish, will decay to 0. Okay, but it could be within minus 1 to plus 1, not only 0 to 1. Okay, so if alpha is within 0 to 1, then continuously it is decreasing, exponentially it is decreasing. So first one will be W0, next one will be alpha times W0, then alpha square W0, then alpha q W0, like that. So it is decreasing. Okay, and if the alpha is positive, so all time, if initial value is positive, every time it is remaining positive, but magnitude is reducing. Okay, so eventually it will become 0. Next one, if alpha is within minus 1 to 0, then also it will converge. You see, if initially it is positive, next time it will be alpha times W0, and alpha itself is negative, so its value will become negative, but magnitude is less than W0. Similarly, it is alpha square W0, then alpha q W0. So alternate positive and negative, but it is going towards 0. It is converging to 0. Right? So we'll put on condition on alpha that if alpha is within minus 1 to plus 1, then this recursive equation will converge to 0. Right. So not only this, if we have this kind of recursive equation, the Wn plus 1 equals to alpha times Wn plus beta, where alpha and beta, these two are constants, then also we can show that this recursive equation will converge to a finite level under one condition on alpha only. Okay, now how to show that? So what I'll do, so this Wn again I replace by alpha times Wn minus 1. So n is replaced by n minus 1 here. So everywhere. So this is n, this is becoming n minus 1. So it is alpha times n minus 1 and it is remaining beta. So if you simplify it, you will get alpha squared Wn minus 1. This alpha into beta plus beta. If you combine these two, you will get beta times of 1 plus alpha. Okay. So again, I can replace this Wn minus 1 by alpha times Wn minus 2 plus beta. Like this. Okay. Then again, if you simplify, so this will become alpha q w of n minus 2. And here, this alpha squared beta is added with this 1. And beta you can take common. You will get 1 plus alpha squared. So if you continue in this way, then this part will become alpha to the power n plus 1, and this is your w of 0, and this summation will become beta common 1 plus alpha square and up to alpha to the power n. So this is a GP series, So first term will remain same, and second term we can replace by on GPC's sum of GP series. The first term is 1 and ratio is alpha. So it is 1 minus alpha to the power n plus 1 upon 1 minus alpha. We are assuming that mod of alpha is less than 1. Okay, and this is beta. Right? So you see this recursive equation again. With this condition -1 to +1, this part alpha to the power n plus 1 will become 0, because this part is with this condition, this is becoming 0, and as well as this is becoming 0. Okay, so this term will vanish, and here this term will vanish. Only you will get at infinity, at limit n tends to infinity, Wn, you will get beta numerator upon 1 minus alpha. So this is your steady state value. It is not 0 exactly, okay, but it will converge to a finite level. Okay, so you see Wn is converging to a finite level. With this condition, alpha is within -1 to +1. It does not depend on beta, but depending on beta, it will attain certain finite level, and that value is for this recursive equation. So that also we can calculate in that way, that suppose its finite level is w of infinity. So I can put this is also infinity, w infinity, this is also w infinity. Both are same at infinity level. Then we can combine these two together. 1 minus alpha w of infinity equals to beta. Then w of infinity will be beta upon 1 minus alpha. Same value we will get. Okay. So it implies that this recursive equation will converge with one condition only, that is with respect to alpha, not on beta. So alpha should be within -1 to +1, and beta can take any value, positive, negative, or any value. But depending on beta, you will get final value, that is your beta upon 1 minus alpha. Right. Anyway, so we have considered one recursive equation with only one variable, Wn, and this Wn plus 1 is depending on only Wn, previous value, and some constant. That is fine. But if I consider this kind of recursive equation, that W0 n plus 1, W1 n plus 1, there are L such equation, and first equation contains like this: W0 n plus 1 equals to some constant times W0n, some constant times W1n, like that, some constant times WL minus 1n. Means this is a linear equation, and W0n plus 1 depends on previous values of W0n, W1n, WL minus 1n, all the things, and it's a linear combinations. Okay, similarly second equation and last equation, all the L equations, they are depending each others. Now if we want to find that whether this W0n or W1n or WL minus 1n, they are converging to certain level or not, that is not easy to find, because you can't concentrate on a single equation. So from this first equation, I can't say that W0n will converge, because it is depending on other variables. This is one problem with this one. So if it is depending on its own variable, then it is absolutely fine. We can say that this value, if it is within +1 to -1, then it will converge. But as other terms are also there, it's not easy to say that W0n will converge to 0 with the condition only R00. Right? So these equations we can make in this form. We can make a column vectors: W0n plus 1, W1n plus 1, WL minus 1n plus 1. And right side, I can consider W0n, W1n, WL minus 1n, this one. And here we can make one matrix. And you see, the first equation will be W0n plus 1 equals to R00 times W0n, R001 times W1n, and similarly R02 times W2n, and last term will be R0, L minus 1 times WL minus 1N. Similarly, the second row and last row. Right? So this is in matrix form. We can rewrite. So if I call this is one column vector, that is your Wn vector underscore I have put here, and this is our matrix capital R. If I call it, then this one I can call obviously Wn plus 1 vector. Okay, so this one I can call Wn plus 1 vector. So I can write in the compact form that Wn plus 1 vector will be equals to R times Wn, right? So this is the compact form, Wn plus 1 equals to R times Wn. Remember, this is a column vector, this is a column vector, and this R is your matrix, square matrix. But we can't solve this W0n, W1n, WL minus 1n independently from single one equations. Okay, so we need to consider all the equations simultaneously to solve this problem, right? But if I have this kind of things that okay, W0n plus 1 is having only relation with W0n, some coefficient, and all other terms are 0, it is not depending on other variables. Similarly, W1n n plus 1 is depending on only W1n with some coefficient, and all other coefficients are zeros. Similarly, last term is having dependence on these terms only, and all other terms coefficients are zeros. Then we can solve all the equations independently. Okay, so you see the problem. So this equation we can solve it easily. Means that if this is diagonal matrix, so left side again we can form a matrix form, vector form, W0n plus 1, W1n plus 1, WL minus 1n plus 1, this column vector. And here I'll get our matrix that will become a diagonal matrix times this W0, W1, W2, this column vector. Then no issue. But if R is not diagonal, then it is problematic. Okay, so there we can use eigenvalue decomposition to make a diagonal form. Okay, let us see that procedure. So this is the vector, and if this is this one, this of this form, a diagonal form, and this is another vector, so this is your Wn plus 1, this is your Wn vector. So if it's diagonal, then easily we can solve it independently, right? Okay, so what do we consider right now? Wn plus 1 vector equals to R times Wn, where R is not diagonal matrix. So we need to solve it. So what we'll do, we replace this capital R by its eigenvalue decomposition, and we replace this R by Q times capital lambda times Q transpose. We know that what is Q? Q is actually the matrix containing all the eigenvectors of R matrix in a column wise form. Okay, one after another we'll get Q, and capital lambda is corresponding diagonal matrix containing all the corresponding eigenvalues. Fine. So this Wn plus 1 vector, so this R is replaced by Q capital lambda Q transpose, and this is your Wn, right? Okay, so what I'll do now, I'll multiply both sides by Q transpose first, left side. Okay, so Q transpose is multiplied left side here, and here also I'll multiply Q transpose here. So here is Q transpose times Wn plus 1. Here Q transpose times Q capital lambda Q transpose and Wn, right? Now this one. So Q transpose Q, already we know that one property, that Q transpose Q is identity matrix, and we have considered that all the eigenvectors are having unity norm. Thus, this Q is orthonormal. So Q transpose Q is identity matrix. This property I am using. So I think property number 6. And this is your capital lambda. and is Q transpose Wn. So if you replace it, so I is, okay, I can remove this I because I times capital lambda is remaining capital lambda. So Q transpose Wn plus 1 will become capital lambda matrix, diagonal matrix times Q transpose Wn. Now, if I consider this one, Q transpose Wn as another variable, Vn, another vector Vn. So this we can consider as transformation. Okay, Q transpose Wn is one transformation on Wn to get new vector Vn. So if I get this is Vn, similarly this one we can call it V of n plus 1 because Q is one constant matrix, right? So this one easily we can say that it is V of n plus 1. So left side is V n plus 1, right side is capital lambda times Vn. Okay, so that we can consider here, where Vn is this one, this transformation, Q transpose Wn, and capital lambda is this diagonal matrix. Now this one easily we can solve it because here all the equations are independent to each other. L equations we will find, but every equation will be independent, and we can say that each element will converge if and only if all the corresponding coefficients are within -1 to +1. So I can say that Vn will converge to 0 null vector as n is approaching to infinity if this lambda I is within -1 to +1 for all I. Okay, here we have to consider all the eigenvalues of this R matrix, and if all the eigenvalues are within -1 to +1, then only every element of Vn will converge to 0. Okay, and if Vn vector is converged to null vector, then obviously I can say that Wn vector is also going to converge to null vector because Q is a constant matrix. That's all, right? Okay. So that was one application for eigenvalue decomposition. We'll be using that concept frequently in adaptation processing, okay, to analyze the algorithms like least mean square, NLMS algorithm, like that. Okay. Now I'll give you one alternative form of eigenvalue decomposition that would be also used in this course sometimes. So we understand that this R can be replaced by Q times capital lambda times Q transpose. Now Q is basically this matrix containing Q0, Q1, QL minus 1, these are all the eigenvectors here, one after another, column wise. And capital lambda is this diagonal matrix. And so Q transpose, we can write, this is it transpose. So Q0 transpose, it will become a row. Okay, next Q1 transpose, next row. Then Q2 transpose, third row. Like that, QL minus 1 transpose will last row. Again, you will find a matrix with dimension L cross L, but this is the orientation, right? Now, if I consider this one first, if I multiply this diagonal matrix with this one, so this is your L cross L, again this is L cross L, the product will remain L cross L. But that time this lambda 0 is multiplied, so this lambda 0 will be multiplied with only this one every time, this row, first row, and second row will be multiplied by lambda 1, third row will be multiplied by lambda 2, like that. So you will be getting this thing that lambda 0 times Q0 transpose, lambda 1 times Q1 transpose, lambda L minus 1 times QL transpose. We can write in this form, this product. Okay, now this and this, okay, if I multiply these two, then what you can write, so this element is multiplied with this one, this element is multiplied with this one, then we'll add. No, that is one way to write it. So what we'll get, this lambda 0 times Q0 times Q0 transpose. Similarly, lambda 1 times Q1 and Q1 transpose. And last time will be lambda L minus 1 times QL minus 1, QL minus 1 transpose. Remember, This is not a scalar quantity. This Q0 is a vector, column vector, and Q0 transpose is a row vector. So column vector L cross 1, okay, and this is 1 cross L, row vector. If you multiply these two, you'll get again L cross L, the square matrix. So lambda 0 times this square matrix, lambda 1 times this square matrix, similarly lambda L minus 1 times this square matrix. Then all the square matrix with this weightage, if you sum it up, you'll get total R. So R we can decompose in this form as well, corresponding to the weightage of eigenvalues and corresponding square matrix. Okay. So this form. Therefore, this R can be also written as lambda I times Qy and Qi transpose, where I will be for all values 0 to L minus 1. So this form is also sometimes useful. Especially we will be discussing to analyze this eigenvalue decomposition, analyze the algorithms like NLMS algorithm, normalized least mean square algorithm by some Slock's model. Okay, there we'll use this concept. So we'll discuss in detail this form later. Okay. If you have enjoyed this video, then you may subscribe this channel. You'll find lots of videos, and to subscribe this channel you can press the subscription button first, and then don't forget to press the bell button, then only you'll get immediate notification of my future videos. And if you really enjoy this video, then you can put a like, and I'll request all of you to share these videos to your nearest one, and if you know that they may need this video and it will be helpful to them, so please share with them. I hope you are going to subscribe this channel if you have not done yet. Thank you.